Welcome to CH225 course on Statistical Data Analysis for Chemists. I am your instructor, Anil Kumar. These are my contact details. This is video 17 in this series. In this video, we will learn about probability and random variables. Inferential statistics is built on the foundation of probability theory and has been remarkably successful in guiding opinion about the conclusions to be drawn from data. Therefore, it is important to have good foundation in probability theory. As we go along in this course, the importance of probability theory and inferential statistics become apparent. Before we discuss any further, let me point out the concepts, which you should be knowing, in probability theory, from your previous learnings. I request each one of you to make sure you refresh your memory about these terms, in case you have forgotten. First is the permutation, which helps in determining the number of ways and distinct objects taken or at a time can be arranged. Here the order of selection is important. In many problems, we are interested in the number of ways of selecting R objects from N without regard to order. These selections are called combinations. You should also need to know how to represent different combinations of various probabilities using Venn diagrams. One should also know how to calculate the conditional probabilities, as well as Bayes' theorem. Now, we move on to learn about random variables. A random variable is a rule that assigns a numerical value to each possible outcome of a random experiment. It is random in nature as its value is not known until we perform the experiment and note the outcome. It is a variable because it can take one of many numerical values based on the outcome of the experiment. Random variable can be either discrete or continuous. Discrete variables rely on counting, and continuous variables rely on measurement. Please refer to video 4 for more details on discrete and continuous variables. Before we go any further, it is important to understand some important terms, which we will be using in this course. The first term is sample. A sample is a set of data, taken from a large data set, called population. This means, the population is the set of all possible outcomes, if the experiment is performed infinite, or large number of times. Let us understand this with an example. Assume you have to find out the percentage of students who smoke in IIT Bombay. In this situation, the population is all the students of IIT Bombay. On the other hand, a sample will be the number of students selected for the survey. Therefore, the sample is a subset of the population. In probability theory, the probability of various outcomes for a limited number of trials will be a sample, and the population will be the probability of various outcomes if the experiment is performed infinite number of times. We also use a term called a sample space in probability. It should be noted that a sample space is nothing but a collection or a set of possible outcomes of a random experiment. For example, roll a die, then the sample space will be all the possible outcomes, and that is 1, 2, 3, 4, 5, and 6. We also use different notations for various statistics when describing a sample set or a population set. These are also provided here. For mean, we use a bar over the random variable for the sample, as shown here as x bar. In the case of population, we use mu. For variance, we use S square for the sample variance and sigma square for population variance. For standard deviation, we use S for the sample and sigma for population. Let us now get back to learning about random variables. We start with the discrete random variable. Since the value of a random variable is determined by the outcome of the experiment, we may assign probabilities of its possible values. For example, let x denote the random variable, that is defined as the sum of two fair dice. In this experiment, the random variable x can take on any integral value between 2 and 12. We can also calculate the probability of each outcome. These are shown here, along with the sample space, for each value of random variable. Since x must take on some value, we must have the sum of all probabilities to be equal to 1. A table, as shown here, listing the values of random variable, along with its probability, is nothing but a probability distribution table. This can also be represented using a bar chart, as shown here. The cumulative distribution function, or more simply the distribution function, f, of the random variable x, is defined for any real number x, can be written as shown here. Wherein f of x is the probability that the random variable x takes on a value that is less than or equal to x. All probability questions about x can be answered in terms of its distribution function, f. For example, suppose we wanted to compute the probability of x greater than a but less than equal to b. This can be easily computed as shown here. The cumulative distribution function f can be expressed in terms of p of x as shown here. If x is a discrete random variable, then its distribution function f is a step function as shown here. That is, the value of f is constant in the intervals, and then takes a step or jump. In case of a continuous random variable, the probability is the area under the curve. Therefore, summation sign of the discrete random variable is replaced by the integration sign, in case of continuous variable, as shown here. Similarly, we can write the cumulative distribution function also, for the continuous random variable, as shown here. It is important to note that the probability a continuous random variable will assume any particular value is 0. Please note that a normal distribution is an example of continuous variable. In subsequent sections, we will be discussing how to find out the probabilities in case of normal distributions.